All right, let's get started. Yesterday we left off on this example with this partial fraction example. So what we're doing in this problem is we're getting the state space representation of this mass damper system. And then we identified the states, we placed in the state space equation, and then we applied the state space to transfer function equation to get that. And then I added a second part to this example where I said, let's give the unit step impulse with no initial conditions and assume K, M, and B are all one. And then we plugged it in, and then we did partial fraction expansion, and we figured out the terms. And then now we're almost at the end of this problem where we are trying to expand this term here into a form that's recognizable. And basically, to do that, we need to combine properties 4 and plug it into property 6 or property 7, I mean. So the reason why I'm doing that is because let's say if I were to apply I think it might be easier to work backwards. If I were to apply property 2.2 property 4 to property 7, so if I were to apply a frequency shift, little side note, maybe I'll right here. So if I apply 2.2 number 4 into table 2.1, which is this top table here, number 7. Let's say I were to apply a frequency shift. Basically, what I'm doing is e to the at cosine omega t. If I were to take the Laplace transform of that, I would get s plus a divided by s plus a squared plus omega squared. Think of it as like if I'm substituting, s with s plus a, we can still use this property, and then we're just adding a shift by a real number. And that's what the time delay does, or the frequency shift does. So that's what we're trying to do right here. We're trying to get this form into that. So now that we have that, we can actually see that we have a frequency shift of 0.5. So e to the minus 0.5 t. And on top of that, we can see that omega squared is equal to 0.75. So then the next step is we can see that omega squared is equal to square root of 0.75. So 3/4, which is equal to sorry. So then omega is equal to square root of 3 divided by 2. Great. So then now that we know that, we just need to get this right term here to match property 6. So basically what we need is we need some constant k. We need some constant k multiplied by 0.5 divided by s plus 0.5 squared plus 0.75. We need that equal to omega divided by s plus 0.5 squared plus 0.7 plus omega squared. And we already know that omega squared is equal to 0.75. So then we sub in omega, we get √3/2 divided by s plus 0.5 squared plus 0.75. So basically some k multiplied by 0.5 is equal to √3/2. I'm just checking my work here. Yep. So then basically what we can do is we solve for that. We get √3. Actually, sorry, I actually approached this the wrong way. We want k is equal to we plot k and we want this to be √3/2, which is equal to 0.5. There you go. So then once we solve for k, apologies for that, we get k is equal to, let's see, inverse of that. It's going to be 1/2 multiplied by 2/√3, which is equal to 1/√3. There you go. Yeah. Okay. So then could I explain my steps? Yeah. I might have just overcomplicated that or made it more confusing, but basically I need to pull some constant k out of here because what I want is oh, we'll just redo that. Move that down. Basically, I want this. I want 0.5 divided by s plus 0.5 squared plus 0.75 to be equal to some constant k, because what we're doing is we're trying to manipulate the term such that we have omega in the numerator instead. So we have √3/2 divided by s plus 0.5 squared plus 0.75. So when we have this form, this here is actually going to be, when we take the inverse Laplace, we get e to the minus 0.5 t multiplied by sine of √3/2t. But then we need to figure out what this k is because these two terms are equivalent. So that's what I did here. And then we find that k is equal to 1/√3. Okay, so now that we know that, we just need to plug these two back into, let's see, this equation here. Yeah. So basically what we have is this. Y of s is equal to 1/s minus, so this is a minus sign right here. So it's going to be minus, let's see, s plus 0.5 divided by s plus 0.5 squared plus 0.75 minus 1 over root 3 times s plus 0, or sorry, 0 root 3 over 2 divided by s plus 0.5 squared plus 0.75. And now that we have that, we can take the inverse Laplace transform. And we get inverse Laplace transform of a step function. 1 over s is just 1. Minus e to the negative 0.5t, because that's the property number 4, the frequency shift, multiplied by property 7, which is cosine times root 3 divided by 2t minus 1 over root 3 multiplied by e to the negative 0.5t multiplied by sine of root 3 divided by 2t. So this is my response due to a step input. Are there any questions? The solution? The complete solution? So this is the complete solution because there are no initial conditions. So this is the force response here. But it's also the total response because there's no initial conditions, where the total response is going to include that, and we didn't have that in here. So we think about this solution here. So this is equal to y of t. And let's check the intuition. If you were to push this mass spring damper with a force of 1 Newton and you're holding it there, the oscillation is going to die out because of the damping, right? So then as y of t goes to infinity, our solution goes to 1 because this exponential term makes the oscillation term decay. Does that make sense? And then if we think about it as well at steady state, meaning nothing is moving, that means x dot, probably at infinity, or I'll say xss is equal to 0. X double dot at steady state is equal to 0. Then that means in our differential equation is x dot double dot plus x dot plus x is equal to f of t. Well, at steady state, we just get x is equal to f of t, which is equal to 1 because it's a step input. So this is another intuition check. Does that answer your question originally?
Starting of the solution to the
Starting,
end.
oh, you want me to just go through the whole example again? Yeah, let's do that. So, okay, so basically what we did here was I have a mass spring damper, and I want to find the transfer function. So while I'm finding the transfer function, I'm ignoring the initial conditions, and I want to formulate this differential equation into a transfer function using state space representation. We can also do it using Laplace transform, but we're covering state space this chapter instead. So what we're doing first is we formulated our ordinary differential equation. It's a second derivative, meaning that we have two states, x dot and x, which is the position and velocity, because the acceleration is dependent on position and acceleration. Once we identified the states, we then applied our state space equation, where we're able to formulate our A, B, C, D matrices, where our main differential equation goes in the bottom row right here, where x double dot is equal to our ordinary differential equation. The top row is just a redundant equation saying velocity is equal to velocity. The thing about the A matrix is that it tells you how the acceleration is related to position velocity. So A matrix basically tells you how the states are connected. The B matrix tells you how the input is applied. In this case, it's 1 over mass. The mass is basically a way of reducing the load of that force. Our C matrix is how we decide our output is going to be measured. So sometimes our sensors limit our C matrix. Sometimes our sensor can only measure velocity or acceleration. We actually can't measure position. So we choose our C matrix based off of that. And the D matrix is if we want our input to appear in our output, which typically in this class it's going to be 0. But for completeness, we included that in here. Once we got our state space representation, we then applied our state space to transfer function equation. It's just a matrix multiplication. You just have to find the inverse of SI minus A. Inverse for a 2x2 matrix is pretty easy. On the exams, I will only give you a 2x2 matrix if you have to invert it. I won't have you invert a 3x3 or higher matrix. And so you can use this trick on the right-hand side. So once we got the state space representation, then I applied a step input, set all the variables K, M, and B equal to 1, just to make it easy. So we plugged this in, and we have our output response, but it's not in the form we recognize. We have to do partial fraction expansion to then break things up into a form that we can recognize. So we can use table 2.1 to take the inverse Laplace transform. We're able to do that for 1 over S, which is the step input. But then for this polynomial that we were not able to factorize, we have to basically kind of do like complete the square method and break it up into a form where it's a combination of property number 4 in table 2.2 and property 7 in table 2.1. Once we got that, we're able to take the inverse Laplace transform and get this final answer, which is the total response. Yeah, question. Yeah. Yeah. So basically what I'm trying to do is so this is what we have on the left. And then this blue one is what we want. The reason why we want that is because this is omega and this is omega squared, which is what we want here. We want omega in the numerator and omega squared in the denominator. Yeah. But then to do that, we're manipulating the numerator. We had to multiply it by some constant to right here for this to be true, for the left hand side and right hand side to be true, because they're no longer the same without pulling some constant out. Yeah, it's not perfectly matched. It's almost matched. Yeah. Yeah, no problem. So that's the example here. Before we continue, I'm going to just code this up in MATLAB, just to show you like how I would do it in MATLAB and to also check our answer. I'll write down the notes in MATLAB and stuff too and upload the MATLAB code. I'm going to close all that. All right. Oh, and I'll share my laptop screen right now. So I'm just going to basically, we'll start from the state space, and I'll just give you the state space right here. Hold on, let me pull it up. Okay. All right. So I'm going to find my variables. K is equal to 1, which is our spring coefficient. B is equal to 1, and M is equal to 1. And then I'm going to find my state variables. So maybe I'll write a note now. Defining state variables. Or not state variables, state space, which is A, B, C, D. And then basically for my A matrix, it was 0, 1, and then minus K divided by M. Yeah, I'll put a comma there. And then minus B divided by M. So those are my A matrix. My B matrix is going to be a column vector, which is 0 and 1 over M. My C matrix is going to be 1, 0. My D matrix is just a constant. So now that's my state space. Oops. There you go. All right. Now, the command I'm going to do is I'm going to use state space to transfer function. So use state space to transfer function to convert A, B, C, D into a transfer function. And if you do help SS2TF, it'll give you documentation on how this works. So you recognize that equation there. That's our state space transfer function equation. And the output is actually the coefficients, the numerator and denominator coefficients. So basically, I want to use num denominator is equal to state space to transfer function A, B, C, D. This here is our input. We can specify how many inputs we have. For single input, single output systems, you don't need to specify it. So let's just run it first and see if this all runs. Okay, so here we can see that we have denominator, our numerator terms. So then what I have to do is now I have to put this into our system. So I'm going to call this G system is equal to TF, which is the transfer function command. And it's going to take these polynomials, or not polynomials, coefficients, and puts it into the transfer function form. Oh, let's take a look. So there you go. 1 over s squared plus s plus 1. Same as what we got. Now, to simulate our response for a step input, there's multiple ways. One is that we actually have a built-in step command. We just type in step gsys, we get this. So it's a unit step input. This is a unit step input. Now, if we want to have a non-unit step input, all you have to do is you multiply. If I want to have a 5-step input, right? I just multiply this by 5. So it's no longer a unit step, but you can see now it's 5 times bigger. So it scales like that because it's a linear operation. Okay. So that's a way to simulate it, but let's compare this to our actual analytical solution. So our actual analytical solution is this. I'm gonna write it down. So this is gonna be a little bit more work, but hold on. Let's see how long this simulation runs for. Goes up to 12 seconds. All right. So I'm going to create a time span from. I'm also live coding this, so if it doesn't work, it's because I'm like live coding it. Let's do from 0 to 12 seconds. Let's do 12. Let's do 10 points per. Yeah, 10 points per second. So this creates an array of time of t. Yeah, array of time. I'll write it out. Okay, and then I'm going to define y out as our solution that we found. And our solution is going to be 1 minus, I believe it's exponential. Not E. Yep, exponential. Just double checking. Exponential of minus 0.5 times t times cosine. And here, cosine's in radians. SQRT, oh, that's latex. SQRT of 3 square root of 3 divided by 2 times t. And actually, we can pull out the exponential because both the cosine and sine terms have it. Minus 1 divided by square root of 3 times sine of square root of 3 divided by 2 times t. Oh boy, is that one too many parentheses? No, I think we're good. All right, let's just run it first and see what happens. I have a bunch of, I knew it. Because I have t here. All right, let's do that. And then check out this trick. Change it all to t-span now. All right, let's try it again. See if it runs. Of course it doesn't. It's because I'm doing array on array multiplication, so I need to put a little dot there. Hopefully that works. Oops, this way. This way, right? Let's see if that works. Yeah, there we go. Okay, so it works, and we have 121 points. All right. This is our actual solution, and let's compare it. I really hope it lines up. Let's try this again. Figure, step, GSys. Actually, we'll just put the actual solution above this. So this is our analytical solution. And then let's plot this out. Let's create a legend. MATLAB step solution, and then this is our math solution. I hope it matches. No, it doesn't match. Where did I go wrong?
Is it the last part?
Yeah, I'm missing it might be missing something right here. Cosine square root of 3 divided by 2 times t-span minus 1 over square root of 3 times sine of square root of 3 divided by. Okay. So I actually did this slightly differently. In my original example, I just did SQRT of 0.75. So I actually have a different solution. Should be the same actually, but I deviated from my notes a little bit today. I mean, it look really lame if it doesn't work. No, let's not save it. And still the same. Interesting. Yeah, I guess I look like a fool today. That's okay. Can't win every day. I'll take a look at this code, but it's a good thing I have a backup from last year that I can run. Since I've done this for so many years now, I'm going to shamelessly pull up my demo from last year. Oh, I actually never did that. Okay. You know what that means? That means my analytical solution could be wrong. So we're going to forget about that for now. I may go back and take a look at the analytical solution. But yeah, that's one way of doing it. Let's say instead of if I give you a input and you need to simulate let's see. That's just your strike number 1. Yeah, 3 strikes, I'm out. Someone else can teach. So
Another way of simulating a step input is creating an array of ones. So basically I can create an array of ones. I'm going to do it to the size of T span. And then what you can do is you can, let's see, how did I do that? T span ones. I'll just be safe instead. I'll just do T span of 121. So this is my step input. And then basically what I want to do is I can say y LSIM is equal to, so this is called LSIM. Basically I put in my system, G system, and then this is first command is going to be use step. Second one's going to be my time, which is T span. And so the reason why I like LSIM more than step is because if you look at LSIM, the input for it allows you to have input, time, and your initial conditions. So this is a simulation where you can also plug in the initial conditions. How you do it is you just put in a array with your initial conditions. So in this case, if we have x is equal to 1 and velocity equal to 1, then we can plug that in. So we'll just do this first, and then we can do this. Try this. Hold on, and then plot this. T span y LSIM. Okay, let's hope this one matches. Otherwise, I'll be very embarrassed. All right, so these two match up because you can't see. They match up because they're overlapped. But let's say I give a initial condition. Now I call it x naught is equal to, let's give initial condition 2 and maybe a velocity of -1. Then I can plug it into here. I believe it should be either a column vector or row vector. I don't remember. We'll see if MATLAB gets angry at me. Okay. Didn't work. Oh, I know why. I can't use G system here. They're very picky about it. G state space. For LSIM, you need to use the state space command instead of transfer function. I don't know why MATLAB's just picky like that. There you go. So now we can see that we have a different response. Let me zoom out. Initial condition starting at 2 with a negative velocity. You can see that my initial trajectory is at 2 and it dips down because of that negative velocity, because it's counteracting that force, but that force is still pushing it towards 1. So it still converges to 1. All right, so I'll upload this code. This is how I would code something live, and maybe I'll just add some more notes. This is my unit step input. This is my initial conditions this is using state space command. And the reason why LSIM, now I might know why. The reason why LSIM likes state space and not transfer function is because the transfer function command only looks at the input response and doesn't look at the initial condition response. That's why LSIM won't work with transfer function if you try to do initial conditions. So use state space command. Then this is what state space looks like. It just puts your variable into the state space and tells you it's a continuum time state space model. So I know it's like I just gave you a lot of different things, but this is how I code live. So it's a little bit easier to follow, and I'll upload this. Are there any questions? And there are 2 comments. Right now, I am not in the notes. I'm just coding live. So I'm going to head back to the notes now.
I understand that you're coding live, but you're coding live, and does that reference what we just did?
Yeah, so basically I was just coding our example to show you what it looks like on MATLAB.
Okay, thanks.
Okay, so now we can move on. So this is why is state space form useful? I mean, if we were looking at the solutions to these differential equations, this one's easy. It's just an exponential decay. So we use like e to the minus at is the solution. There's four different units. There's four different solutions here. For a second order system, we saw we can have oscillation, we can have decay, we can have decay with oscillation, we can have very fast decay, basically. Third order, it just starts getting messy. You just can't really solve by guessing. Fourth order, same. And any higher order, it's just hard to solve for it. So the reason why we like state space representation is because like any higher order or any higher order differential equation can be expressed as a first order differential equation in matrix form. So yeah, state space equation or state equations takes higher ODE and turns it into a first order differential equation in matrix form. And that's to the effect of x dot is equal to ax plus bu. And this is a first order differential equation in matrix form, and that's why we love it. And then the solution to a first order differential equation is this. X of t is equal to e to the minus at, and that's for that's the natural solution. And that's why we like it. So, oh yeah, there's the punchline because we can put higher order differential equations into a first order differential equation in matrix form. It's just very, very powerful. So let's go over this example. Yeah. Yes, exactly. Exactly. So yeah, so question is like as we increase the number of the order, we're increasing the rank of vase. So the number of different possible solution increases. It does increase, and it's just hard to find it just by guessing.
Variables that are like different derivatives of x that negative other state variables, and that's the same effect. Is that
Yeah. Yeah, exactly. So if we have the other day, someone mentioned if we have a mass with another mass. So when we just have one mass, it's 1 degree of freedom. Now that we have two masses, we have 2 degrees of freedom. So then now we have, like, let's call this mass 1, x1, and this mass 2, x2. Now we actually have x1 up to double dot and x2 up to double dot. So we now have a 4x4 A matrix because we have 2 state variables from here and 2 state variables from here. So it's 2 state variables each. So you get a total of 4 now. Okay, so now we were to find the state space for this generic form here, where we have so right here we have y, and we have up to the nth derivative. Basically, we can rewrite this as y to the nth derivative is equal to minus a n minus 1, y to the n minus 1 derivative, minus all the way down to a1 y to the first derivative, plus or minus a0 y plus b naught u. And basically we now have end state variables. We have end state variables. And what we want to do is we want to put this into a we want to put this into a state space equation. So let's first define our state variables. So I'm going to call x is equal to x1, x2, all the way down to xn. And I'm going to define x1 as y, x2 as y to the first derivative, all the way to xn, which is going to be y n minus 1. And then when I take the derivative, I get x dot. So I guess this state vector is equal to x1 dot, which is equal to y first derivative, which is actually equal to x2. x2 dot is equal to y to the second derivative, which is actually going to be equal to x3. All the way down to, let's go to xn minus 1 dot, which is going to be equal to y to the n minus 1, yep, which is equal to xn. Yep, just had to think about that for a second. And then x dot n, which is equal to yn. Okay. So the reason why I did that is because I want to put this differential into state space form where basically I want x dot is equal to ax plus bu. So I had to define x dot and x here. So we're going to do that on the next page. I'll bring this with me. So just making space. Here you go. Okay. So I'll write this out again and write this fully. It's going to be x1 dot, x2 dot, we'll go to x3 dot. All the way down to x dot n minus 1 to x dot n. And we're going to have a really big matrix for this. We have x1, x2, x3, all the way to xn minus 1 and xn. Plus my B matrix multiplied by U. All right. X1 dot is equal to x2. So it's going to be 0, 1, 0. And it's going to be zeros for the rest of the rows. X2 dot is equal to x3. So it's 0, 1, 0, 0, 1, all the way down, and then zeros for the rest of the rows, columns. So then we repeat this pattern. Basically, we have ones in the off diagonals. And basically, the ones is going to be on this off diagonal ending here. So then the second to last row is 0, 0, 0. Then it's going to be down to, let me make this bit more obvious like that. There you go. So we have the ones in this off diagonal here, and this 0 here is the 0 diagonal. And then for the last row, we need our differential equation. So I'll take this differential equation. Put it down here. Another way of looking at it, it's going to be yn is equal to minus an minus 1 xn minus dot dot minus, let's see, a1 x2 minus a0 x1 plus b naught u. So basically what I just did here was I just replaced the y's with my definitions of my state variables. And then when I fill in this table, it's going to be minus a0 because it's a0 x1 minus a1 minus a2. This is going to go all the way to minus an minus 2 minus an minus 1. And then here in my B column, we don't have any inputs until here, which is B naught. Okay, and then this is my state equation. Are there any questions? Okay, so the thing about this differential equation, about this equation here, because we know the solution to a first order differential equation, but in the matrix form, there's a special case. The solution exists. The solution for initial condition, like initial condition response, x of t is going to be equal to e to the minus at multiplied by the initial condition. That's the solution. It exists if A is invertible. Invertible exists. So this only works if we have an invertible A matrix. That's a little side note about this. And the other thing about the state space form is that this is not the only form that we can express this system. So just because we have a transfer function, like in the previous example, we can have different representation of that same transfer function in state space form. So we can move some numbers in this A matrix. We can move it into, we can transpose it, and then we can move some terms into the B and C matrices, and they'll be the same system. So state space representation is not unique. And you'll see that in homework too. Any questions? Okay. So I have another example, but I think I'll leave it for next class. I was actually hoping I could get through this today, but I guess not. So we're going to wrap up chapter 3 on Monday. I have uploaded chapter 4, which is on poles and zeros. That's going to be our first really long chapter. And by the end of next week, that should be it on new material before midterm 1 as well. Mainly up to the end of next week will be material that will cover, that will be covered on the first midterm. Homework 1 is due today, and homework 2 has been uploaded already. This second homework is a little bit tedious. The last 3 problems are a little bit tedious. First 2 should hopefully be straightforward. So I would start a little bit earlier. And I'll have office hours right after this at MEB 236 at 11:30. So, yep. Thank you.